Hello everyone. In this video we will see about the forward kinematics of manipulators by using a DH formulation approach. So here first we will see what is roll, pitch and yaw moments. In this video you can see the differentiation. So this is the pitch moment, this is roll and this is yaw. Okay, so roll, pitch and yaw. So we know that a roll moment is along so pitch is y-axis and roll is z-axis and yaw is x-axis. Okay, so now we'll see RPY rest. Okay, so you know this RPY rest can be described using the DH parameters as well. Okay, so this is also known as XYZ Euler rest. Okay, it's a common part of end effector or rest design used in robotic manipulators. So it allows for rotations about x, y and z axis. So which correspond to the roll, pitch and yaw angles. You know this. To calculate the forward kinematics of an RPY rest, so we need to determine the transformation matrix uh, which relates the end effector frame to the base frame based on the given RPY angles. Okay, so first we will see this RPY rest moment. So this is roll, could see roll, x-axis, and this is y-axis pitch. And this is z-axis yaw. Okay, so these are RPY rest movements. Okay, so this RPY rest can be described using the DH parameters as well. Okay, so that is Dynavit-Hartenberg parameters. To compute the forward kinematics using the DH parameters for RPY rest, first we need to define the DH parameters for each of the three rotational joints. So you know you have roll, pitch and yaw here. Okay, so how will you represent the DH parameters for RPY rest and calculate the forward kinematics? First we'll be assigning the joints, naming the joints. Okay, so here we name the joints as, that is, you have 0, 1, 2, 3, so from base to the end effector. Okay, so we are going to compute the roll, pitch and yaw movements. Okay, so here you could see the frame assignment for 3 degree of freedom RPY rest. So the axis of will be along the z-axis. Okay, so first how will you compute the DH parameter by using forward kinematics is, so along I'll say in general, then we'll see the DH parameter table. Okay, so along the roll, okay, here there is no link length, so it is 0, and here degrees of rotation about x-axis you have to see, that is here the parameter is alpha. So you know that you have to calculate 4 parameters, right? So that is the link length and degrees, that is alpha, and offset and theta, the roll angle. Okay, you have to calculate all this. So here according to the roll joint there is no link length and rotation about x-axis is here 90 degrees, that is minus pi by 2, and there is no offset, so that is also 0, and theta is there. Okay, so theta is along theta 1. Then about pitch, here also there is no link length. Okay, so everything is on the same plane, so there is no link length for all the three rotations, three revolute joints. So there is no link length and no rotation about the x-axis and no offset. Okay, so pitch angle is there, that is theta 2. And yaw joint, no link length, and we have a 90 degrees rotation about x-axis, no offset, and yaw angle is there along theta 3. Okay, so this is in general. So how will you compute in by using a DH parameter table is, could see here the frame assignment of this RPO wrist. So first along the link here, it is the all the three joints are considered as 1, 2, and 3. So first along the link 1, okay, you could see here, so the four parameters are theta, d, a, and alpha. Okay, so theta is the angle along the common axis, that is z axis, so you have here as theta 1. Okay, so here, and there is no offset, so it is 0, and no link length, that is a. Okay, offset is d and a is link length, that is also 0. So alpha is here rotation about x-axis, so that is 90 degrees. Okay, and next link 2. So link 2 here, the angle. Okay, so here we have angle along rotation about the z-axis is here already. Z-axis should be this plane, but so it is moving around this plane. So how will you compute the angle is that it is theta 2, angle is theta 2 plus 90. Okay, so it has to calculate it about rotation about that is the pitch angle. Okay, so you will have theta 2 plus 90. Okay, so here again there is no offset and there is no link length, but we have the pitch angle. Okay, that is as 90 degree. And then along yaw moment, so here we have yaw angle, that is theta 3 along z axis, so z axis along this common normal. Okay, so here again there is no link length and no offset. We have there is no degrees of rotation along the x-axis. Okay, so that is also 0. So this is how DH parameter table is formed. So this along the common normal, that is z-axis, we have to check. And first we will be forming the DH parameter table, and we know how to calculate the transformation matrix. Okay, we have a transformation matrix for this to compute, and accordingly what are the parameters needed in that, that is cos theta, sin theta, alpha I, cos alpha, sin alpha. Okay, so based on that I am computing the cos theta, sin theta, cos alpha, and sin alpha. Okay, with which I have those parameters, and finally put together you will have the complete table. Okay, this is for solving the problem easily. So only DH parameter table is important, and this is the transformation matrix, that is the homogeneous transformation matrix for cross 4 for the DH parameter approach. Okay, so we have to calculate the each transformation. So this is the transformation matrix for roll. Okay, and next transformation matrix for pitch, and transformation matrix for yaw. So we will be calculating, previously we have a n plus 1, right? So we have to substitute n is equal to 0, 1, and 2. So you will get t1, t2, and t3. Okay, so for for getting the transformation matrix, we have to multiply all the overall transformation matrix for the RP So if you multiply all the three matrices, you will get the overall transformation matrix for this. Okay. And next, about the forward kinematics of a 4 degree of freedom SCARA robot. Okay. So here we have a 4-axis horizontal jointed articulated arm configuration. So which means we have here sliding joint as well as rotational joint is present. So first two are revolute joints. Okay, you could see here in the horizontal portion of the tool. So first two are revolute joints. So third is the prismatic joint. Okay, first two are rotational. So RR, and third is the prismatic. So vertical position of the tool. So we have that is P, and fourth is again revolute joint. So which controls the tool orientation. You could see here by using this theta representation. So theta 1, theta 2 are the revolute joints. Okay, and third link you have, that is a prismatic joint, and fourth is again theta 4 we have. Okay, so this is the RR PR configuration. So this is represented as RR PR configuration SCARA robot. Okay, so for this first we have to form the TH parameter table. I have named the link. So here we have, it's a rotation, but you have here link 1 and link 2 I have named, and here you have in between this link 1 and link 2 the prismatic joint. Okay, that is the vertical portion of the tool movement, is I have named it as L12. Okay, so this link 1 and link 2 is named as L11, L12. So you have here 4 axes, axis 1, 2, axis 4. Okay, this and we have here link 4, we know that. Okay, so link 0 is a base link, link 1, link 2, and link 3 and link 4. You could see in the picture. Okay, next, for forming this DH parameter table, you need 4 parameters: theta, that is length of a set D, and link length A, and alpha. Okay, so you could see the axis here. So axis of rotation along the x-axis and z-axis we have to check, right? So first DH. So here we have RRPR configuration. So first is link 1. So in this we know that this is the rotation. So we have obviously theta is there. So theta 1, and the offset. So offset is present as a offset between the link 1 and link 2. We have L12. Okay, and link length is here for this is L11, and there is no angle along the x-axis. Okay, there is no rotation about x-axis, so alpha is 0. Next, coming to link 2. Okay, so here again this is about the revolute rotational axis, so it is theta 2, and there is no offset, so 0, and here link length is L2, and no degrees of rotation along the about the x-axis. Okay, so again it is 0. Next, coming to prismatic. Okay, so prismatic is obviously we have the sliding moment, so we don't have any angle, theta is not there, so it is 0, and the prismatic moment we have, this is D3, represented as D3. Okay, and link length is here, it is not present, so it is 0, and so degrees rotation, that is rotation about x-axis along this link 3 is, you could see here 90 plus 90, that is 180. Okay, so we have here as 180 degree. And next, coming to the fourth link, so here again there is revolute RRPR configuration. Okay, so it is revolute joint rotation. So obviously we have the angle as theta 4, And also here we have the tool moment, right? So we have the uh, offset as L4. Offset is present L4, and link length is not there, 0, and there is no rotation about x-axis. Okay, so it is 0. So this is the DH parameter table, and after this will be for computation of this transformation matrix, we'll calculate the cos theta, sin theta, and sin alpha and cos alpha. Okay. To make the calculation easier, we're forming this table. This is for your understanding. Okay, it's not mandatory. And coming to this we know that 4 cross 4 homogeneous transformation matrix for the DH table. Okay, so combination of this table, this will give you. So we'll have here 4 transformation matrix. So you will be substituting first here n is 0, 1, 2, 1, 3. Okay, so you will get the transformation matrix, 4 transformation matrix, and if you multiply this all the transformation matrix, we will get the overall transformation matrix. Okay. So what is this in transformation matrix? What is this represented as? 1, 2, 4, C1, 2, 4, S1, 2, 4 is expansion is given. So that is C1 is 1 is theta 1 and theta 2. Okay, and theta 4. Okay, so how it is named as it is expansion is given. Okay, so matrix in the form of a simplification one, expansion is given for all the uh, C and S. Okay, that is cos and sine. Okay, so that is all about the forward kinematics approach for by using DH parameter approach. Okay, we have seen RPA wrist configuration and 4 degree of freedom SCARA robot. Okay, thank you.